Okay, so today let us discuss more on applications of Bayes theorem. Okay. So let me recall what it says. Um, so before that, so we want to apply Bayes theorem. I mean, mostly we will be applying Bayes theorem in the context of Noethern subsets. So I think it was not clearly defined. Nirupama's class, it's not clearly defined what is Noethern. So she proved for intersection of open dense subsets of a complete metric space is dense again. So I will recall, or I will say I will define what is a Novak dense subset definition. XD be a metric space. A set F containing X is nowhere dense. Just say NWD. So usually, I mean, see, it is enough for our purpose nowhere dense to be defined for closed subsets. But it is defined more generally. But okay, we can generally define. So what is F is nowhere dense if for all open U contained in X, there exists a Bx epsilon contained in U such that it does not intersect the F, isn't it? If you have any open set, I mean, it's enough if you take open balls. If you take any open ball, there is a further open ball which does not intersect this F. So this is the definition of nowhere dense subset. You can actually prove the following. It's very direct to prove this proposition. F is closed, then F is nowhere dense if and only if interior of F is 0. Interior of F is empty. It's interior of F equal to empty. That means F does not contain any open balls. That's what it means. So proof. One way should be clear. F is, so if it is nowhere dense, it cannot contain any open ball. If it contains open ball, then that cannot have a further open ball which does not intersect with that, because the open ball itself is contained. So one way is clear. If it is nowhere dense, this way is clear. If it is nowhere dense, then interior is empty. So we want to prove this way. So suppose interior is empty. So suppose interior of a set F is empty. Then we want to prove it is nowhere dense. Then let U contained in X be open. Then we want to prove that there is a further open. So first thing is U cannot be contained in F, of course, because U is not U. Because if it contains, it will contain open ball, of course, not contained in F. So there exists a X in U and B X epsilon such that there exists X in U, which is not there. Right? There exists X in U such that X is not in F, right? That's what I'm saying. So U is not contained in F, so there exists X in U which is not in F. Okay. Then since F is closed means it contains all its limit points. So X is not in F means it's not a limit point. It's not a limit point means there exists a epsilon greater than 0 such that maybe epsilon 1 greater than 0 such that B of X epsilon 1 intersection F is empty, right? If such a epsilon 1 does not exist, then then X becomes a limit point. So which is not the case. So this is the case. Okay. On the other hand, since x is in U, there exists a b x epsilon 2, which is contained in U. Okay. So there exists, I mean, let epsilon equal to epsilon 1 minimum, epsilon 2, then b of x epsilon intersection f, which is contained in U and intersection f is it. Okay. So this proves that for nowhere dense subset, it is enough that the interior is empty and interior is empty. So that is enough to prove that. So we will assume that as our definition for the time being for our application. For all our application, that is enough. So a set is closed. I mean, by nowhere dense means the set is closed and it does not have any interior. Okay. So this has many applications, and Nirupama has given some assignments. I haven't looked at it yet. But I think it has something about so let me just say this proposition. I think this is part of the assignment. Any infinite dimensional Banach space, Banach space means complete, cannot have finite, not finite, countable Hamel basis. Hamel basis means it's algebraic basis. I mean, it is the finite linear combination of elements in the basis should be equal to that. So the basis should generate algebraically. Finite linear combination should generate. Of course, if you want to take infinite linear combination, then you have to specify a topology. So that's a analytic statement. It's not a algebraic statement. So Hamel basis means algebraically it should generate the whole thing, which is not possible. So if you have any basis, then you take finitely countable basis, then you take finitely many of them, I mean up to n of them. Then you take the space generated by that, show that it is no, oh, I have to say what is the Baire categories theorem. Sorry, I have to recall Baire categories theorem. I will come back to this. This is anyway assignment. I will explain this. So the Baire's theorem is the following. X is complete. Okay. Then and UN contained in X, which is open and dense. Okay. Then intersection of UN is also dense. Is dense in X. So if you take open and dense subsets, if you take the intersection, that is also dense here. So if Fn is nowhere dense, Fn contained in. So on the other way, if suppose maybe you call it corollary if you want. Fn, so X complete as before. Fn contained in X, nowhere dense means closed and interior is, I mean closed to nowhere dense. Okay. So then Fn complement is open and dense. The complement of nowhere dense is dense. I have to connect with the laptop. So the complement of nowhere dense subset is dense. I mean, a nowhere dense subset cannot contain an open ball. So every open ball will intersect with the complement. So that's what dense means. Okay. The dense means you can find a sequence which converges to that. But if you take, I mean, that you can do. If you take sequence depends on 1 by n or something. If you take any bx 1 by n, that will have something in the complement and that will converge to that. To every element in X, there will be a sequence in the whatever we call it dense subset, there will be a sequence converging to that, that you can form if every open set intersects with that. So every Fn complement Fn cannot contain any closed set, means every open ball will intersect Fn complement, so it is dense. So this is open and dense. So this implies intersection of Fn complement is dense. So this implies union of Fn complement is dense in X. So in particular, this is not a non-empty. Or this is union of Fn complement is a proper subset. A proper subset. It's contained in the, it's a proper subset. So this is what is called first category. Any set which can be written as, oh my God. Any set which can be written as countable union of nowhere dense subsets. Uncountable union, of course, you can write any set as uncountable union of any singleton or something. So that's not the point. So any set which can be written as countable union of nowhere dense subsets, that's what is called a first category. So a complete metric space is not a first category. That's what this is. Okay. So and anything which is not first category, second category. Okay. So any complete metric space, the statement it follows is any complete metric space is not a first category. Is second category. So this is the theorem. Usually this is called as Bayes' theorem, if you want. So in particular, you have this Bayes. Where did I reach? Yeah, any complete metric space, second category. So yeah, so if you have an infinite dimensional Banach space, then if you take any finite dimensional subspace, so if you take any subspace generated by finitely many elements, which is a finite dimensional subspace, that is nowhere dense. Of course, finite dimensional subspace is closed and it is nowhere dense. It cannot contain an open ball. That if you take, so if you can't find an open ball around origin in a subspace, then you can't find an open ball around any point, because every open ball will be a translation of that. So around origin, if you take any open ball, then it will contain all elements which are norm less than X, that will exist everywhere. I mean, that will exist outside the subspace also, the open ball. So it can, I mean, you can just use that and prove that assignment. Okay. So that is one immediate application. Infinite dimensional Banach space cannot have a countable basis. Next thing is, if you, so next we can apply this to, for example, to what are called perfect sets. So let me state it. Okay, let me start with definitions. I don't know whether you know what is perfect set, so let me recall. So let F contained in X. X is some metric space. Okay. Then X element of X element of X is enough. X is an accumulation point. Point for F. If for all epsilon greater than 0, B of X epsilon intersects with that is not equal to empty. Okay. Answer minus X. I mean, for all open balls, the point X is removed from that. Okay. The B of X epsilon minus singleton X. So you remove that singleton X. I mean, there should be an intersection with F, which is not that X. So that is what is called an accumulation point. A limit point is without that condition, that something is without that condition. That I mean, it is just B X epsilon, which intersects. That is what is definition of limit point. So this accumulation point is slightly different. Okay, every accumulation point is a limit point, but a limit point may not be an accumulation point. So this is definition. So next definition is a set is perfect set F contained in X is perfect set, perfect if F is equal to all its accumulation points. So that is what is called a perfect set. So now the proposition is the application of Baer category theorem is any perfect set is uncountable. Yeah, any perfect set is closed, of course. No, any perfect set need not be closed, no, because you can have a limit point which is not an accumulation point. Should I need closed perfect set? I think so, maybe. So you can have set of just two single point, then that does not have an accumulation point, right? But it is closed. So you can have a single point that does not have an accumulation point, that has a limit point, singleton set. So any closed, so a perfect set is, let's assume that a perfect set is closed and it's, if F is closed and F is equal to all of them. Okay, so then any perfect set is uncountable. I mean, we only want to apply the Bayes theorem. Okay, how would this is applied? The proof is immediate. You assume that singleton X is not open. So it is nowhere dense. I mean, singleton X can be open in general, because when it is a isolated point, it can be open. Okay, if you take any open ball in a, I mean, we can see, the point is, let us consider the set itself as a, see, suppose F contained in X is a X is complete. So we need X should be complete also. So we need X is complete. Any perfect set of a complete metric space. X is complete, F is closed. Okay. Then F is also complete and it's on its own as a metric space on its own. Okay. F is a complete metric space on its own. On its own. Okay. And in that, in F, singleton X is not open because it's a perfect set. Okay. If you have any, I mean, singleton, it has to be an isolated point, because you have to have an open ball around X which is contained in the set, means the open ball has to be singleton X. So it should not intersect with that. That is not possible because it has all its accumulation point. Okay. So because of that, this is not open, and but it anyway closed. Okay, this is closed. So it is nowhere dense. When it is not open, and singleton X is closed and nowhere dense. I mean, it's nowhere dense is enough. So it's nowhere dense. Now F cannot be written as, I mean, F is equal to union of singleton X and F. So F cannot be countable. F is uncountable. Okay. Anyway, these are all some, we will see more applications of this. I will give some more assignments. So today we will talk about the nowhere differentiable functions, which forms a second category in the space of all continuous functions. That's what we will do. And then there are more applications. For example, if you take a sequence of continuous functions, then if the convergence is, if you say a sequence of continuous function which converges to some F, if the convergence is uniform, then the limit is also continuous. But in general, if it is just point-wise convergence, then it is not continuous. But still, you can prove that the point of discontinuities are just countable. You can prove that. So that you can prove using Baire category theorem. So I will give that as an assignment, but I will give all the possible hints, and then ask you to do that. So, I mean, this semester I will give more assignments, so there will be more weightage in the grade for assignments. So that we will do as an assignment. Then there are all this closed graph theorem, open mapping theorem, uniform boundedness principle. They are all applications of this Baire category theorem only. So we will see more applications later. Okay, now we will talk about what are called the nowhere differentiable functions. Okay, so what do you want to do? So see, if you take C01, we know that all continuous functions. Continuous functions. For instance, if you take this C101, and f prime exists, and it is continuous. Is dense here. Okay. Any function can be approximated by a differentiable function. It's not even that you can have infinitely differentiable function that will be dense here. For example, you take polynomials, you can approximate everything by polynomial. So the polynomial is infinitely differentiable. So, and the derivative is also continuous. So, I mean, all derivatives are continuous. So differentiable functions are dense. They are everywhere dense. But still, see, the density doesn't mean anything about the number of elements. That number of elements is something. It can be infinite, but there are difference. Rational numbers are dense in real numbers. Irrational numbers are also dense in real numbers, but irrational numbers are too bigger than, I mean, they are uncountable. Okay, you cannot have countable union of rational numbers to get into. You cannot associate countable union of rational numbers for irrational numbers. So it is too big. It's like a power set of rational numbers. So similarly, even though differentiable functions, infinitely differentiable functions are dense here, the even functions which are differentiable at one point, I mean, there exists a point where it is differentiable. Even such functions forms a very small, small set inside C01. Small sets means it's a first category. Okay, so that is what we want to prove. So if we want to prove that, this is the theorem we want to prove is the following. The so-called nowhere differentiable function, the functions which are not differentiable at any point. So it will be, you can't draw the graph, it will be very bizarre. Okay, nowhere differentiable functions contained in C01 forms a second category. Okay. So that is what we want to prove today. So to prove that, we will do the following. We will start with so what we will do, we will prove that the functions which are differentiable at one point, that forms a first category. Okay, that can be written as union of nowhere dense subsets. That's what we want to prove. Okay, so let t equal to all those f in C of 01, C01, and f is differentiable at some point for at some x in 01. Okay. So we want to prove that this set is a meager set. It's a first category set. That's what we want to prove. To prove that, we define a set A, N, and M. For N and M in natural numbers, positive integers, we define the following. So there exists X in F in. It is the collection of these kind of functions. 0, 1. There exists x in, there exists a x in zero one, such that f of t minus f of x by t minus x mod of this is less than n for all t minus x less than that. I mean, it should be delta, so 1 by n. Okay. So I'm just defining this set. I'm taking all those functions for which there exists some x. Okay, this bounded condition is satisfied. There exists some x where this ratio, I mean, this quotient, whatever ratio, f of t minus f of x divided by t minus x. I mean, if t goes to x, this will be the derivative, right? So the derivative is bounded kind of thing. Okay, so f of t minus f of x, t minus x. I mean, if derivative exists, then this should happen, right? If derivative exists at x, then the derivative is some value f prime x. Okay, so this will be near f, this value, whatever the less than n I have written, f prime x should be less than some n. It's a number, real number. So this should be near that. So this condition should be satisfied for some n, for some t minus x, because that limit exists, that for t minus x less than 1 by n, this should be satisfied. Okay. So if somewhere this limit exists, then I mean somewhere the derivative exists, then this condition should satisfy. Should be satisfied. So this is what I am calling as A and M. And I want to, these are the two claims. A and M is closed. So the claims are the following. So proposition A and M. Let's fix the N and M, closed and nowhere dense. I mean, we want to prove nowhere dense, basically closed and it does not have any interior. That's what we want to prove, nowhere dense. So proof. So A and M is closed. First, we want to prove A and M is closed. So to prove that A and M is closed, I take some sequence Fn contained in A. So Fk, maybe there is N and M here. Fk contained in A and M, and Fk converges to F uniformly, of course. They converge in the norm infinity, so they converge uniformly. Then I want to prove that this F also satisfies this condition. Okay, that's what we want. Okay, so for each k there exists, so for all k there exists a xk. I mean, because since Fk is in A and M, this is what it means. There exists a xk. I'm just rewriting the definition again. There exists a xk such that f of xk, f of t minus f of xk, maybe f of t minus f of xk divided by t minus xk. This modulus is less than n for all t minus xk. This modulus is less than 1. That's what this satisfies. But then this xk are contained in the compact set 0, 1. Okay, this xk. So this is sequentially compact. So there exists a x such that xk converges to x. So without loss of generality, I mean, you can take a subsequence if you want. Assume that's, I mean, without loss of generality, without loss of generality, I'm taking this. Xk, see this 0, 1 is sequentially compact. So there will exist a subsequence of xk which will converge to some x. So without loss of generality, if you want, you take the subsequence and work with that. Okay, because we already know f is there, it's enough to show that some subsequence will also converge. We want to show f is in this, so it's enough to take a subsequence. Okay, so without loss of generality, assume is compact. Assume without loss of generality that there exists a x such that xk converges to x. Okay. This is okay. Okay. Now f of xk converges to. Now we want to write. What do you want to write? We want to write this f of. I have written something wrong here. Fk this, fk this. Right. This should be fk. Okay. This should be right now. Now, yeah, fk of xk will also converge to f of x. You can work with that. Integral, say, modulus of f of t minus f of x divided by t minus x t minus x is equal to limit, everything is continuous function, limit of f of fk of t minus fk of xk divided by t minus xk. It is just the epsilon by 3 trick or something. Fk by fk of xk will converge to f of x. Because, I mean, it's all continuous function. F of xk will converge to f of x, xk converges to this, and use, I mean, this is just the epsilon by 3 trick. Okay, using that, this is the next exercise. +2 exercise. Okay. So because of that, this limit will be there, and so the whole thing is less than a. What is the notation used? I use script A or ordinary A. This is okay. Is okay, no? Is okay. Okay, I don't see any answer. I assume it's okay. How many of you? Yeah. Okay, I hope you are listening. I see many people. Okay, I hope it's okay. 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 So this is okay. Close this okay. So now all I have to prove that it is the interior of ANM is empty. So to prove that the interior of ANM is empty, of course, it means that there does not exist any open ball inside that. So I take any F in ANM, I take any open ball or any epsilon open ball around that, it has to intersect with the complement. That means it does not satisfy that condition, right? It does not satisfy this boundedness condition we have used. So now to prove ANM is, what's the time? Nowhere dense, that is interior of ANM equal to empty. Choose some open ball B of f epsilon for Fn A. I completely forgot to prove something. So let us do this first. Okay, this is a lemma. Before going to that, I want to do this lemma. Maybe I should use definition first. I mean, I hope you know what is piecewise linear function. Okay, so this is definition. P contained in C01. Set of piecewise linear function. Piecewise linear functions. That is, there exists x naught equal to x less than x1 less than x2 up to less than xn equal to 1, such that the function is linear. It's just a straight line. I mean, the function is, I mean, any straight line gives a function. Is the straight line joining the function is straight line joining xi f of xi and xi plus 1 f of xi plus 1. So p of xi plus 1. I mean, you have to know the value of p at all these points, n points. Okay, p of x, what is p of x1, p of x2 up there. Then you can just, I mean, then there is only one function which is a straight line joining these two things in this interval, xi plus 1. Okay, and it will be a different straight line in different places. So it will be like this. This is not straight line. It will be like this. Okay, whatever. Yeah, it will be a piecewise straight line like this. So where these are all the points, the nodes are the points xi, I mean, or the point xi f of xi. This point is xi plus 1 f of xi plus 1. So once you know these 2 points, then there is one straight line joining these two things, and you know the function. So this is what is that. So if you know this, so this is what is called piecewise linear function. And this is of course differentiable everywhere except those finite points, x1 up to xn. So now the lemma is this p contained in C01. Of course, they are all continuous, but they are not differentiable at all points. They are, I mean, except finite, they are differentiable everywhere except those finite points. Is dense. Oof. So let f be any function in C01. Okay. Then f is continuous, so it's uniformly continuous because C01 is compact. So then f is uniformly continuous since uniformly continuous. There exists delta continuous for all epsilon greater than 0. There exists delta less than 0 such that f of x minus y, f of x minus f of y is less than epsilon if x minus y is less than delta. Okay. So this is satisfied because it's uniformly continuous function. Now choose x naught equal to 0, less than x1, less than x2, less than xn equal to 1, such that xi plus 1 minus xi is less than delta. Okay. For all n. And define p from 0, 1, c. R is unknown. We working with R or C? I mean, let us work with R because we want to talk about differentiability. No? So C, I mean, it will be just a 2 variable function. That doesn't matter. So we assume that this is R. Okay, our field is R. There is no difference between C and R. Since I am using all this straight line and all those things, let me call the field to this. We define P to R by P of xi equal to f of xi. Okay. And P restricted to this interval xi plus 1 is straight line. Okay. Once you know P of xi equal to f of xi, then you can just join this as straight lines. Now this approximates that. Now let's forget about now. P of x for any x, P of x minus f of x is less than or equal to f of x. X is in some xi. Any x is going to be in xi plus 1. F of x minus f of xi, let's say, plus f of xi minus p of xi. But f of x equal to p of xi, so we can change this to now. This is less than or equal to f of x minus f of x. This f of x minus f of xi. I mean, xi minus xi plus x. The distance between xi and xi plus 1 is less than delta. So the distance between x and xi plus 1 is also less than delta. So f of x minus f of xy is less than epsilon. Okay. And this is p of xi. This is less than p of xi minus p of xi plus 1. I mean, this is a straight line. Okay, in a straight line, if you, I mean, there is a parametric form of a straight line or something. You can start from a point and you can write it as the distance. So along the straight line, x has a larger distance from xi. I mean, x has a shorter distance from xi than xi plus 1. Okay, so this is true. That p of xi, is that right? Maybe it will be multiplied by a thing. This is clear. Okay, check. I mean, you have to write it if they don't want to write it. This is clear. Okay? Because it's just on a straight line. You may have a sine theta, cos theta. You may have to multiply by a slope or something. Okay. Up to that, so p of xi minus p of xi plus 1, which is just the y part of that. And when this distance, I mean, it's clear. If you draw the diagram, draw the triangle, it will be clear. Okay. So because of this, this whole thing is less than 2 epsilon. So we have proved that every continuous function can be approximated by a piecewise linear function. So this is what we will use here. So what do we want to prove? We want to prove that we wanted to prove that nowhere differentiable functions forms the second category. So somewhere differentiable function, a function which is differentiable at a point, is our first category. For that, I defined the set A and M. A and M is defined by this condition, f of t minus f of x by t minus x is less than m. I have proved that A and M is closed. Now I want to prove that A and M is also nowhere dense. I mean, it does not contain any interior. That's what I want to prove. So I want to prove that it does not contain any open ball inside that. Okay. So let F is in A and M and consider this. The open ball of epsilon radius around that. So I want to prove that this is not contained in A and M. That is, this intersects with the complement of that. So that is, I have to prove that there is a element in this open ball which does not satisfy this condition. Okay, that's what I want. I want to get a G, want a G in C01 such that the infinity norm of f of minus G is less than epsilon, and G does not satisfy that condition. I'll call that condition star or something. This condition is called a star. Okay. Does not satisfy star. That is, for something in that 1 by m region, x minus t is less than 1 by m, that f of t minus f of x divided by x minus t, that should be greater than that n. That's what you want. Okay, you want to get it. Now, first to choose a p, which is a piecewise linear function, such that now f minus p is less than epsilon. Okay. you will get something in terms of epsilon. I mean, if you want to get epsilon finally, then you have to divide it by, maybe take this epsilon by 2, next one by divided by something. So we will do it later. Okay. Okay. We choose some this divided by this. Okay. Now we are P is a piecewise linear function. Okay. Now let the slope of, see, there is something that, so let m is the, let p prime x is bounded. See, I mean, P has derivatives. I mean, the P prime X is bounded, of course, because they are not differentiable at few. I mean, P prime X is less than M for, I mean, for X in, for a, for P differentiable at X. Okay. I mean, it's not differentiable at finitely many points. So P differentiable at X. Okay. For all those points, this is less. There are finitely many slopes. It's a piecewise linear functional, and there are finitely many slopes, and on that it's going to be bounded. Okay. So P prime is less than M. So for some K, I mean, we have to, so depending upon this M and that N and then N, the small m and small n we already have. Depending upon all that, we'll choose a K. Okay. For some K, I mean positive, choose a G in P such that G of X is less than 1, less than or equal to 1, maybe less than 1 for all X 0, 1, and G prime X is equal to plus or minus K for all X, and not for all X, for all X in 0, 1 where differentiable. I mean, this is a piecewise linear function, so except finite points will be differentiable where G is differentiable. Wherever it is differentiable, the derivative is just plus or minus K. Okay, I mean, the derivative is going to be a constant, and that constant is plus or minus K, or where K we are free to choose. You can always choose such a function. That's what I'm saying. So this can be done as follows. For instance, choose 0 equal to, choose AI equal to I by K. I by K, and then G of AI. So we want it to be less than 1, G of AI equal to 0. I mean, for I even. Assume 0 is even, and equal to 1 for I odd. So I equal to 0, 1 up to K minus 1, right? So we have partitioned the interval 0, 1. Okay. And we have defined G of AI to be 0 and 1, where for even thing it is 0, and for I thing it's minus 1. So it will go like this. Okay. And the slope will be K, right? Plus or minus K. If it is this way, it is K. This way, I mean, on the other, where it is decreasing, it is minus K. This function will work. Check. I mean, you just draw it, it will be clear. Okay. Right. Now take H equal to P plus G. then H is differentiable except finitely many points. Okay. And what do we want to do? We want to prove that and wherever it is differentiable, it is h prime x. Okay, wherever it is differentiable is equal to, of course, p prime x plus g prime x. Okay, mod of this is equal to p prime x plus or minus that k. Sorry, I should take an epsilon here. Then only epsilon g. Okay, so there will be an epsilon here. There will be epsilon k. Okay, that will work. So now we know that p prime x is less than or equal to m. Okay, and if we choose, we haven't chosen this k. Okay, for each k I have done this. If we choose this k, I mean, we should have chosen earlier, but still, then I want to make sure what is that epsilon. So maybe I take this as epsilon by 2, f minus p is epsilon by 2. And here also I'm taking this epsilon by 2. Epsilon by 2. And if we choose k such that k is greater than or equal to, the epsilon should come down 2 times. So we want this to be greater than, this is m. So this will be greater than that m. So it will be, so epsilon will be divided, 2 epsilon by 2 will be divided. And we want still to be less greater than m. Yeah, right? Okay. Since this p prime x is less than m, and if we choose our k greater than this, okay, we can choose any k, okay, greater than this, then this h prime x will be greater than n, right? Is that right? Okay, wherever x is differentiable. And there will be near every, I mean, there are finitely many points where it's not differentiable, but you will find a x which is differentiable there. So this implies for all, see, we have to find, so there exists a, and we have a L, we have a M here. So there exists a 1 by L less than 1 by M, okay, such that G of t less than minus g of x minus t minus x is greater than n if t minus x is less than it's not contained. What should I write for not contained? Is this okay? Shall I repeat anything? See, the point is any function can be approximated by a piecewise linear function. Then that piecewise linear functional, you can add another piecewise linear functional by multiplying by epsilon. So you don't really increase the norm. See, this approximation, this f minus p is in terms of infinity norm. Without increasing the norm, so that if you add that function, the norm will be increased by some epsilon by 2 only. But that piecewise functional, you can have any slope you want. Okay, between 0, you can partition it as, I mean, you can partition it as much as you want. I mean, you can take a coarser partition of the 0, 1, and within that partition, you can have draw steep lines. with the, with slope this k, so that it comes down and with minus k, okay, so that the resulting that g which you have added to this original p, which approximates that f, okay, that will have a very big slope, so that you can add to any of these things, that it will be larger than our n we want. So that is what I have done. So if you have any more questions, you can ask me. But I think I have written the details here. We just go through it, it will be clear. Okay. So now, whatever did I say D or something? What did I say? Yeah, D equal to f function differentiable at some point. Okay, that is D. Now that D, so here this proof ends. Now D equal to union of NM, AN. Right. It should be bounded for something. So each ANM is nowhere done. So this implies D is first determinant. So this implies nowhere dense functions forms a second category in the set of all, in the space of all continuous function. So I will give some assignment on some, as I said, the discontinuity of continuous limit, point-wise limit of continuous function, and maybe one more on this Baire category theorem, and we will see more on Baire category theorem relating to functional analysis. Okay. So with this, I stop here. If you have questions, you can ask. Otherwise, I will stop.
So when is the assignment submission?
You can, as I said, it's better you write it each week and then you submit it before the midterm. If you start writing near the midterm exam, you will not have time for midterm exam. You will have all the exams. No? So it's better to write it now and then submit it before midterm exam.
Okay, thank you.
So